right, welcome back. So last time I promised that we would talk about the stuff remaining on Wednesday, but now I'm still in COVID protocol. It's time because of my daughter, but things happen. It's okay. So last time we were talking about retarding forces, specifically air resistance, and more specifically, we're talking about velocity-dependent forces. So as we wrote down last time, that simply means that the net external force plus then the drag force must be equal to the mass times the acceleration, which in this case we're writing as the velocity, the time rate of change of the velocity. So now we want to start looking at another type of example. So here I'm going to look at now vertical motion. So let's start looking at vertical motion. So last time we looked at horizontal motion, which we made one-dimensionally. We can say which is only moving horizontally, for example. We made that a one-dimensional problem. So here we want to do the same thing. Let's start looking at a one-dimensional motion, but again, now in the vertical situation. So now let's take a concrete example. So let's say here's my mass m, and now this guy is going to be moving with initial velocity, let's say downward. Okay, so here's my initial velocity. And let's go ahead and choose then that my positive x direction is downward since it's moving in the downward direction. So in this case, that means that what our drag force is going to be upward. This is our drag force. And then, of course, we have the gravitational force pulling it down. So we do that green. So this is then my ND down in this direction. So this is our concrete example. Let's work off of this guy. So again, we want to do what we did last time, and we want to look at this guy from the two different viewpoints. So meaning that we're going to look at it first from the linear motion, or sorry, linear resistance, and the linear drag. And then we'll look at it from the quadratic drag. So great. Now, before we start talking, let's again look at our expectations. So what should we actually expect in this case? Now, of course, the details of this are going to depend ultimately on the initial velocity. So am I starting off with a small initial velocity? Is it 0? Is it a large initial velocity? So let's for now assume that my initial velocity is small relative to what's called the terminal velocity. So let's say in this case, my initial velocity is less than terminal velocity. We'll talk about what the terminal velocity comes from in this case. So what does this mean? So this means that what initially, if this thing has 0 initial velocity or at least small initial velocity, this thing, of course, will start to fall with minimal effect from the drag force, meaning that this thing is going to fall relatively basically just like free fall, right? Which means then that in that case, our velocity, at least for early times, so let's do it this way. So for early times, we'd expect in that case that our velocity has to then be proportional directly to g times t, right? Because this thing is going to fall basically just like free fall, right, before this drag force has really had an effect on taking away some of the acceleration of the subject. So even if it starts off with a large initial velocity, again, for very, very early kind of times, this thing should be falling pretty much just like free fall, right? It's just going to fall initially at free fall. Now, as time goes on, though, what's going to happen? So as time goes on, what's going to happen then is that my drag force, which initially starts off at 0, is going to increase and increase and increase and increase and increase until eventually it's going to match the size then of the gravitational force, at which stage the acceleration in that case is going to go to 0. Okay? So at late times, what should happen in this case then is that my acceleration should go to 0, which means my velocity then will go to what's called the terminal velocity. So terminal velocity, again, as we talked about in 205, it occurs when the acceleration goes to 0, which in this case means the drag force then is simply equal to the gravitational weight. So what is the drag force? Well, we can determine that or sorry, not the drag force, but we can determine the terminal velocity here in just a second. So the other things, let's write some other expectations down here. So another expectation is that what? At late times then, well, let's look at it early times. So at early times, what this means then is that, again, since the velocity is increasing as g times t, what that means then is that the position then should be increasing quadratically. Right? So for early times then, my position then should be increasing quadratically. And then for late times, what this says then is what? If the velocity goes to a constant, meaning acceleration goes to 0, then that means that what? My position should be increasing only linearly. So in this case, at late times, this means then that my position should then be proportional then simply to my terminal velocity times the time. So this thing should be increasing linearly, again, since I now have constant velocity. So my position just be linearly actually increasing. Oh, good. So next thing is we want to know, what is that terminal velocity? So to get the terminal velocity, we can actually start off with this expression here, and now just fill in the dots. So in this case, we know our external force is going to be mg minus then our linear velocity, or linear drag, which is v1 times v, must then be equal then to mv dots. But in this case, since we want terminal velocity, that occurs when v dot then goes to 0, which means that this guy's just simply 0. Now, when this happens, this thing becomes specifically my terminal velocity. So we're just going to call that my terminal velocity. So solving this says that my terminal velocity then is just going to be mg divided by b1. So this is my terminal velocity. So we'll find this later. But again, this is what my velocity should go to at late times. Right? So just my weight divided by then my coefficients. So good. So let's actually solve this guy. So let's put all this stuff in here. So in this case, what I have then is, let's go back up. So I get an m times dv dt is then equal to mg minus then b1 times v. Now, there's multiple different ways that we can solve this, but the way I want to use here, the way I actually want to solve it, is to use what's known as an integrating factor. So before I do that, first let's divide both sides then by the mass. So I'm going to get dv dt is equal then to g minus b1 over m times v. Or I'm going to rewrite this guy as dv dt is then equal, or sorry, plus b1 m times then v is then equal to g. So what I want to use then is something you should have learned in differential equations, or if you haven't learned in differential equations yet, or if you haven't taken differential equations, or you're taking it now, is what's known as an integrating factor. So let's quickly talk about what an integrating factor is. So an integrating factor says is if I have a differential equation that looks something like what? Y prime, where y prime in this case is just the derivative of y with respect to our parameter. So in this case, say y prime is then equal to dy dx plus some function p of x times then y is equal to some other function, let's call it q of x. Great. Now, what an integrating factor basically does is it says that what? I can multiply both sides of this by a constant, well, not a constant, but as a function. I can multiply both of the sides by what's called mu sub x, where mu sub x then is going to be equal to e to the integral of px dx. Okay? Now, what the integrating factor does is it says, let's multiply both sides by this function here. Okay? Now, why would I care about doing that? So let's actually multiply this out. Let's see what happens. So now if I take mu x y prime plus then p of x mu times y is then equal to q of x times mu. Okay. Now, you may be thinking to yourself, why do I actually care about doing this? Well, notice that what actually happened now is notice that what? The first term here has a derivative of y with respect to x. And then the second term has the derivative of the exponential pulled down in the form of p of x. And then still has the mu, where the mu is simply the exponential times then y. So notice that what's actually happening here is that the left-hand side I can actually rewrite in terms of a total derivative. So this is actually the real main reason that I want to use an integrating factor, is because I can actually rewrite my left-hand side as simply d dx of then mu times y is then equal to the function q of x times u. Right? So again, if I look at my left-hand side, what I'm going to do is I have a product of two functions. So if I take the derivative of the first, I'm going to get the derivative then of the exponential. But again, the derivative of the exponential is then just the exponential back times then the derivative of the exponent, which in this case would be the derivative of the integral, which then just pulls down to p q here, which is actually this term, times then the second function, and then plus then the first function times the derivative of the second function, where the second function is simply y, which is actually then this term. So the nice thing then about using this integrating factor is that all it does is it rewrites my left-hand side then as a total derivative. Now, what's also nice about that is now when I go to integrate, so let's say now what I want to do is integrate both sides of this by simply multiplying by dx on both sides and then integrating. Now what that does then is it kills off the dx here, so that now what happens then is what? When I take the integral of d mu y, well, that's the same thing as simply integrating something like dx, which means that the only thing I get then is my left-hand side simply becomes mu times y. So in this case, I get mu times y evaluated from my initial conditions. So mu y initial to mu y final is then equal to the integral of then my right-hand side. So in this case, again, what I can do is I can always rewrite this thing in terms of this integrating factor, which then turns this left-hand side simply into a total derivative. So let's see how this actually works. So in this case, let's follow what I did here. So comparing my equation on the left in black to the equation on the right, we can see then is that p sub k, or sorry, p sub x in this case, is simply equal to d1n, which means my integrating factor mu is then just e to the integral of b1 over m dt, because in this case I'm doing an t integral, not an x integral. But since b1 over m is simply a constant, this is then the same thing as e to the b1m integral of dt, which is the same thing as t. So this just becomes e b1m times t. So this is then my integrating factor. So now if I multiply both sides of this by my integrating factor, so now I'm going to multiply both sides of this guy by my integrating factor, and then use the same trick that I did on this side here by rewriting it as a total derivative. In this case, I'm now going to have that what d dt, then my integrating factor, which is e b1 over m times t, times my original function, which is v, then must be equal to g times e to the b1 m t. So okay, now what I want to do is simply integrate this guy. So now I'm going to integrate both sides with respect to t, where again, on the left-hand side, the t's cancel, which means I'm simply going to integrate this guy then from the initial conditions, which in this case is going to be from t is equal to 0, as well as v0. So if t is equal to 0, then in that case, I get simply the b1 over mt is that just 0, which is simply 1 times v0. So let's write that out. So what happens then is that my left-hand side is going to become e, the b1t over mv minus v0 then is now going to be equal to g integral e to the b1 over m times t dt integrated from 0 to t. Yeah, let's keep going. So this thing then is going to be equal to what? So the integral of that guy is just going to be divided by him. So I get a gm over b1 e to the b1 t over m evaluated from 0 to t. Pardon me. So let's keep going a little bit further. So that then is going to become equal to mg over b1 times then what? E to the b1t over m minus 1. Good. Now, finally, let's go a little bit further. So what we want is the velocity as a function of time. So let's add v0 to both sides. Let me go ahead and do that. So I'm going to add v0 to both sides. And then finally, what I want to do then is what? Get rid of the exponential here by multiplying by negative of the exponential. So let's go ahead and do that. Finally, what I get then is that v is going to be equal to this way, v0 e to the minus b1t over m. So that's that term. And now I'm going to get a plus mg over b1. And finally, I'm going to get what? Inside, when I multiply by the negative, that cancels out the first term. So I get a 1 minus e to the minus b1t over m. So this then becomes my velocity as a function of time. So good. So let's talk about this guy. So first things first, let's look at our basic limits of this guy. So the first thing is, let's look at the easier of the two. Let's look at the late time limit. So let's look at the late time. So in this case, meaning that's what? T goes off to infinity. So this is my late time limit. So in this case, V is then going to be going equal to, well, if T goes to infinity, the first term here is going to go to 0. So I'm going to get a 0. And I'm going to get plus an mg over b1 times then 1 minus 0, which is all the same thing then as mg divided by b1. But if we backtrack, what we said before was that mg divided by b1 is simply my terminal velocity. So indeed, this thing does go to then my terminal velocity. So as t goes to infinity, this thing goes to my terminal velocity, exactly the same thing we got when we set this guy's equal to. So indeed, as time goes off to infinity, this thing then asymptotes or approaches then my terminal velocity. Now, what about at early times? So early times, in this case, I want then what? My t to be very small, which means that I want my v1t over m to be much, much less than 1, which ultimately then just means that what? T must be much, much less than m over v. So good. So in this case, let's go ahead and do a Taylor series expansion then of our exponential. So in that case, our exponential e to the v1t over m is then going to be approximately equal to 1 minus v1t over m. So let's plug that in then to our velocity. So our velocity then is going to be equal to what? V0 times that guy. So I get a 1 minus v1t over m. Good. Plus then my terminal velocity, which is right at terminal velocity, times then 1 minus v1t over m. Good. So let's keep going. So this guy then is going to become equal to what? So let's write all the notes. So this thing will then be approximately equal to, so I get a V0, then I'm going to get a minus V0 B1 over MT plus my terminal velocity. Actually, yeah, because this guy here is going to cancel this guy, which makes that a plus. Good. Plus my terminal velocity times then B1T over M. Now again, using that dt is equal to mg over b1. This thing then is going to be equal to v0. And then I get a plus g times t from the second term. And then finally I get a minus b0, or sorry, b1, b0, b1 m over t. Now, in this case, I know that's what, according to my approximation, though, the b1t over m is much, much less than 1, which means this term here is basically just going to get 0. So this thing then is approximately just equal to v0 plus gt. So again, at early times, this thing is what? Just again, linearly growing. This thing is simply in free fall, which means that it is only experiencing then the acceleration due to gravity. Great. So what does this mean? So this means that what? If I start off with low velocities, this thing then is going to asymptotically then approach my terminal speed. So in this case, if this is my time, and then this is my velocity, so my initial velocity is somewhere small, where this is say my terminal velocity, then what happens in this case then again is this thing is just going to start off with the initial velocity. Let's say initially my initial velocity is 0, make it a little easier. Then this thing then is going to what? Initially linearly kind of grow, and then it's going to curl over and then follow and asymptotically approach then my terminal velocity. Now, if it starts off with a v0 not equal to 0, so for example, in this case, it'll still do the same thing. So this thing is just going to grow. It's then going to still asymptotically then approach my terminal velocity. And then same thing. So for no matter what initial velocity this thing starts off with, as long as the velocity is less than the terminal velocity, this thing is then just going to, again, asymptotically approach my terminal velocity. Now, what happens though if my initial velocity, so what happens if my initial velocity is greater than my terminal velocity? what happens in this case? Well, basically the same thing happens, right? So ultimately all that's going to happen is if my initial velocity is greater than my terminal velocity, what then happens to the size of my drag force relative to the size of my gravitational force? Well, going back to here, if my initial velocity, again, is greater than my terminal velocity, what's going to happen in that case then is my drag force is actually going to be very, very large compared to the gravitational force, which means that this thing is, again, going to start off with a huge amount of resistance force onto it, causing it to slow down until eventually what'll happen again is that the drag force size, instead of increasing, but will now decrease until it reaches that of the same size as the weight. So in this case, again, now it's the dominant force is now going to be the drag force initially, but as it slows down due to the fact that the net acceleration in this case will be upward, causing it to again asymptote then to the acceleration goes to zero, which means again it's going to asymptote then to the velocity, which is my terminal velocity. So basically, going back to my plot here, so even if I start off with an initial velocity which is greater than my terminal velocity, all that's going to happen is now I'm going to start off somewhere out here with my initial velocity. But this thing now is going to decrease, and then it's going to decay exponentially, basically, until again it's going to asymptote towards that terminal velocity. So again, no matter what this initial velocity is, it's going to asymptote then to this terminal velocity. So good. So this is what happens for the velocity. So no matter what do I start off with, whether it's the initial velocity is greater than or less than my terminal velocity, it's still going to asymptote to that terminal velocity because, again, the size of the drag force will always become equal to the size of the gravitational force, causing the acceleration then to go to zero at that stage. So now let's look at the position as a function of time. So let's go back to our velocity. So we know our velocity then is equal to v initial e to the minus v1t over m plus my terminal velocity, times 1 minus e to the minus v1t over m. Now again, to find a position as a function of time, I know that v here is simply equal to dx dt. So we're going to use our separation of variables, multiply both sides by dt, and then integrate. My left-hand side is going to become x minus x initial is then equal to, I'm going to split this up into two different integrals. So I'm going to get a v0 integral e to the minus v1t over m from 0 to t dt plus vt. So I'm going to split up into three different integrals. So then I get an integral 0 to t dt minus integral e to the minus v1t over m dt from 0 to t. So let's plug those in. So this one, again, all I'm going to get is a negative sign. So I'm going to get a negative v0m over v1 e to the minus v1t over m, evaluated from 0 to t. And then I'm going to get a plus vt times t. So this is my linearly growing term. Good. So this is the one that should dominate again as we go to late times. And then I'm going to get a minus v terminal times m divided by b1 e to the minus, actually I already got a minus in there, so it becomes a plus, sorry. Minus b1t over m evaluated from 0 to t. Good. Now here, again, I can bring in my negative sign, so I'm going to make that a positive. I'm going to switch this to t, make that 0. So this then is going to become equal to v0m over v1 times 1 minus e to the minus v1t over m. Good. And then I'm going to get a plus vtt, and then I'm going to get a plus vtm over v1, and then I'm going to get an e to the minus b1t divided by m minus 1. So this then is my, good. So this is my position as a function of time. Good. So again, first thing to note is that what? So let's look at the late time limit. So again, as the late time limit, as we did before, so as t goes to infinity, what we said was that the velocity simply then goes to what? A constant. So if the velocity goes to a constant, this thing again has to grow linearly with time. So in that case, what's going to happen then is what? The second term in the first term here is just going to go to 0. So my x then is going to become equal to x initial plus v0m over b1, because that second term is going to go to 0, plus vt times t, right? And then here again, that first term is going to go to 0. So then I'm going to get a minus vtm over b1. Good. So pulling some terms together, what I finally get then is I get an x0 plus m over b1 times v0 minus the terminal velocity plus dt times the time. Now again, the important thing to notice here is that what? Again, this thing is going to what? Again, linearly grow as time because of this last term. All other terms are simply then equal to constants. Okay. So finally, let's find the position as a function of velocity, or the velocity as a function of position. So let's go ahead and do that. So again, to redo that, again, remember that our dv/dt, we can rewrite then as dv/dx times then dx dt using our chain rule, which is the same thing as d times dv/dx. So let's go back to our initial points. So in that case, we have a what? Acceleration, or dv/dt. So we get a v dv/dx was equal to x minus, so this is b1 over m times v. So in this case, unfortunately, because this v sits out front here, there's no way we can actually use an integrating factor in this case, because the integrating factor has to have that the derivative is all by itself. So in this case, we can't actually do that. So here we're just going to use separation of variables. So basically all I'm going to do is I'm going to bring everything with a v. So all this stuff here, divide over here, and then multiply by the dx onto this side. So this is going to become v dv over g minus b1 over mv integrated from the initial to the final is then equal to what? Simply dx. Okay? Integrated from x initial to then x final. So for this guy, let's use a u substitution. So u for the left-hand side, I'm going to then rewrite as g minus b1 over m times v, which means that du then is equal to minus b1 m dv. So it's going to be that guy. Good. So from here, let's rewrite the left-hand side. So from this term here, we can rewrite v. So v then is going to become equal to, let's write this guy out. So I'm going to get a m over b1 times g minus u. Okay? So this is my v. So all I did was add the second term to the left-hand side and then subtract the u and then multiply by the inverse of that guy. So that means my left-hand side then is going to become equal to the integral. We'll fill in what the bounds are here in a second. So v, which I'm going to get an m over b1 v, so I'm going to get a g minus u, okay, so that's that term, divided by u, and then finally I get a du, for du I get a minus b1 over m dv. Put that in parentheses, there we go. So that this term here will actually cancel this term, so I'm just going to get the negative sign outside. So good. We'll see why I actually do that in just a second. And then all of that is then equal to x minus x initial. Now, again, let's talk about our bounds. Now, for our bounds, when v is equal to v0, I'm just going to get a g minus b1 over m v0. And then to my later bound, which is g minus b1 over m times v. Yeah, let's simplify that just a little bit further. So notice what I can do now is I can what? Split up the integral on the left-hand side now with two integrals. So I'm going to get a g over u, which is simply a natural log, and then I get a minus u over u, which is the same thing as 1. So let's go ahead and do that. So finally what I get is, so putting all this stuff together, I'm trying to make any math mistakes. Good. So I'm going to get a integral g minus b1 over m v0, g minus b1 over m v. I'm going to pull out the g over here, so then I get a du over u minus, and then I just get the integral g minus b1 over m v0 g minus b1 over mv du is then equal to x minus x initial. But I mentioned this side is simply the natural log, so I'm going to get a g natural log then of what? G minus b1 over mv divided by g minus b1 mv0 minus, so in this case I get what? An integral of du, which is simply u evaluated from here to here. So good. So what's going to happen in this case then is what? My g's here are simply going to cancel. So I'm going to get a minus, so let's leave it this way for now. So I'm going to get a minus, another minus, that gives me a plus, b1 over m, and I get a b minus b initial is then all equal to x minus x initial. Okay. Doing okay? So great. So what does this mean? So basically what this means is this is now going to be my velocity as a function of position. Now notice that this thing is not easy to solve for the velocity. And the reason for that is if you look at it, I now have two pieces here. I have a natural log piece here, and then I also have a linear piece here. So solving this thing is not exactly trivial. Basically, for the most part, you would have to either do this numerically or you would have to look at certain regions where one of these two guys is going to go to maybe not zero, but will be subdominant to the other one. So then you can do an approximate solution to be able to find then the velocity as a function of position. But overall, this is what it actually looks like. So this would be our solution. So again, numerically, this would be easy. So given a particular location, I can then numerically solve for what the velocity is at that particular position. Here, of course, this has the opposite thing. If I know what the velocity is, the initial velocity, I can easily find the position. But again, oppositely, if I numerically do this, I just substitute in what the position is, and then I can numerically find what that particular velocity is. But it's not as nice, not as clean cut as all the other ones we've looked at, but it's a solution. So you can be happy about that. Pardon me. All right, so let's look at the quadratic situation. So let's look at quadratic resistance. So basically, again, let's take exactly the same picture. So here's my plus x-axis going this direction. Again, my gravitational force is acting downwards. So this is g. We know our drag force, again, is going to be upward. So, but in this case, our drag then is going to be the quadratic drag. Good. And then again, our initial velocity, and we do that in gray this time, it's going to be, again, downward just for consistency. So in this case, again, we're going to end up with that's what? M times dv dt is then going to be equal to mg minus now b2 times b squared. This is now going to be my new function I have to solve. Or again, let's rewrite it. Dividing both sides by m, I get a dv dt is equal to g minus then b2 mb squared. Good. Now again, before we start, let's go ahead and look at our expectations just to compare again. I mean, our expectations here should be very similar in the fact that again, at early times, this thing should basically be free fall. Which basically means, again, our velocity should be directly proportional to t. Again, at late times, again, this thing should be constant velocity. So our acceleration should go to zero, which means our velocity should go to terminal velocity. Notice in this case, our terminal velocity is slightly different because of the presence of the square. So again, for terminal velocity, over here, terminal velocity, again, since the acceleration is equal to zero, we now have a g minus b2 over m. The terminal squared is equal to zero, which means our terminal velocity then is going to be mg over b2 squared root. This is going to be our terminal velocity. Slightly different from before, but it's basically the same thing. So again, I mean, our expectations are going to be basically the same, but again, the details are going to be different because now we have a different scenario. Now we have a quadratic velocity instead of a linear velocity, which means that we won't be able to use the integrating factor in this case. And again, it's going to depend on the initial velocity. So again, let's go ahead and solve this guy just for funsies. Now, again, since we can't use an integrating factor, we're just going to use our separation of variables again. So again, all that means is I'm going to divide both sides by the right-hand term and multiply both sides by dt. So ultimately, I'm then going to get that my ed divided by g minus b2 over md squared is then equal to dt. And again, let's integrate both sides. So right-hand side from 0 to t, left-hand side from b initial to then b final. The left-hand side we should note is actually just an arc hyperbolic tangent. So you can find this with Mathematica or look it up in a mathematical notebook or mathematical table or whatever it is that you want to use. But it turns out it's just an arc tangent. So let's put in a solution for that. So this becomes the square root of m over b2g arc hyperbolic tangent of the square root of b2 over mg times b evaluated then from the initial to the final is then equal to t. So plugging in my bounds, what I then get is the square root of m over b2g times inverse hyperbolic tangent, square root of b2mg d minus the inverse hyperbolic tangent or the arc hyperbolic tangent, square root b2mg b0 is then equal to t. Good. Solving this guy for v. Basically, what I have to do is multiply by the coefficient out here, so this guy, and then add the hyperbolic term to the other side, and then take a hyperbolic tangent to both sides, and then divide by this term here. But basically, if I do all that, what I finally get is that my velocity then is the square root of mg divided by b2, where notice this is my terminal velocity up front, times then the hyperbolic tangent of the square root of b2g divided by m times t. Oops, sorry. Plus the inverse hyperbolic tangent of the square root of b2m b0. So this is my velocity as a function of time. So as I said, notice that the front term here is actually just the hyperbolic or just the terminal velocity. So basically, again, what we want to do is look at what happens when time goes off to infinity. To do that, I'm going to make a simplification. I'm simply going to say, well, let v0 equal 0, so that's inverse hyperbolic tangent of 0 is simply 0, so this term is simply going to go to 0, just to make my life a little bit easier. So in that case, then my velocity, again, is just going to be what? The square root of mg over b2 hyperbolic tangent of the square root of b2g over m times t. So basically, what happens then is what? For hyperbolic tangent, this thing asymptotes for large times or large angles or large arguments simply to 1. So basically, what happens then is that what? In the limit that t goes off to infinity, my hyperbolic tangent then of x simply goes to x. Okay? Which basically means in this case, as t goes to infinity, then my velocity then goes as the terminal velocity times then my square root of then b2g divided by m times t, which means that in this case, my velocity then goes as, oh, I'm sorry, I'm doing the wrong limit. This is my small time limit, sorry. So t is, so sorry about that. So this is my square root of b2g over m is times t, sorry. Is much, much less than 1. Sorry about that. So in this case, my hyperbolic tangent goes to x. Sorry. And the limit I was originally talking about, when time goes to infinity, the hyperbolic tangent does go to 1, and we'll do that in just a second. So in this case, let's look at the early time limits. So, sorry, be consistent with what I'm doing. So early time. So in this case, then this guy is going to become, so let's put in our numbers. So it's becomes square root of mg over b2 times the square root of b2g over m1 times t. So basically, m's here are going to cancel. The b2s are going to cancel. I get a g squared square rooted, which is a g, which means this thing goes as g of t. So this thing, again, grows simply linearly in time, like we said it should. Again, for late times, what happens in this case then is that what? Again, the hyperbolic tangent of the argument x as x goes to infinity simply is going to go to 1. It's just property of a hyperbolic tangent. So hyperbolic tangent, if I plotted it, actually this does this, where this is at 1 and this is at -1, which basically means that, again, my velocity is simply going to go to my terminal velocity. Nice. Now, again, this is also going to be true for large times and small times. Or sorry, not large times and small times, but large initial velocities and small initial velocities. Again, same thing applies as we talked about last time. So if the initial velocity is small, it's going to speed up until what happens is that the drag force, again, is going to be equal to the gravitational force. So I'll have terminal velocity. If the initial velocity is greater than the terminal velocity, it's just going to slow down until the same thing happens. So, great. So again, all this means then is if I plotted, again, my velocity versus my time. It's my time, where again, this is my terminal velocity. Again, for small velocities, this thing is just going to asymptote. And then for large velocity, it's also just going to asymptote. So now let's find the position as a function of time. So let's go ahead and work on that. So again, in this case, multiplying through. So my left-hand side is going to be x0 to x dx, then is going to be equal to my terminal velocity integration from 0 to t, then my hyperbolic tangent square root of e to g over mt dt. For this guy, again, I'm just going to use a u substitution. So in this case, let's say u then is equal to hyperbolic cosine of a times t, where a is just that coefficient there, right? So that du then is going to be equal to a times hyperbolic sine of at dt, right? So basically putting that in, so if I take then du divided by u, that's the same thing as my tangent here. So this thing is actually just going to give me a natural log. So I'm going to get an x minus x initial then is equal to my terminal velocity divided by a, because that is divided by both sides here. And then I'm going to get my integral of then du divided by u. So I'm going to get a natural log. And then I'm just going to evaluate u at 0, but hyperbolic cosine at 0 is simply 1, to where this thing is then hyperbolic cosine a sine t. So this thing then is just going to become VTA, natural log then of the hyperbolic cosine a times t. Now, plugging in our value, this is going to be VT times the square root of m divided by b2g times then the natural log of the hyperbolic cosine of the square root of b2g over m times t. So let's talk about this guy. So again, what we said was that what, as time goes off to infinity, the velocity goes to the terminal velocity. So my position should then just, again, linearly grow. Now, to think about this, let's think about what a hyperbolic cosine does. So let's think about hyperbolic cosine. So hyperbolic cosine, what we can do is we can rewrite a hyperbolic cosine. So hyperbolic cosine of a t is the same thing as e to the at plus e to the minus at all divided by 2. Right? Now, let's look at what happens as t goes off to infinity. Well, t goes to infinity, the second term here simply goes to 0, while the first term exists, which means this thing then is going to become e to the at divided by 2. Now, if I ignore that 2 for now, notice that when I take the natural log then of the hyperbolic cosine at, right, in the limit that t then goes off to infinity, this thing then is just going to become the natural log of e to the at, but the natural log of e to the at is simply the same thing as a times t. So in the limit that t then goes off to infinity, what happens in this case then is I get x then is equal to x initial plus my terminal velocity times then the argument simply a times t. Oh, I forgot that first term. times then the square root of m over b2g. Now again, using that a is the same thing as what? The square root of b2g divided by m. So again, what happens when I multiply these out? The m's are going to cancel, the b2s are going to cancel. So this thing is just going to become x0 plus bt times t. So again, in the late time limit, this thing simply grows linearly with time, again, as we said it should. So finally, let's look at the velocity as a function of position. So again, let's do that. So this is going to become v dx, or sorry, dd dx is then equal to g minus b2 over m v squared. Now notice the left-hand side here, we can now pull a trick here, where notice I can rewrite the left-hand side as d dx v squared multiplied by 1/2. So now when I take the derivative of this guy, I'm going to get a 2 down from the derivative times the derivative of v, right, times the derivative of dx. So this thing here is the same thing as him. So that means I'm simply going to rewrite this then as 1/2 d dx of v squared is then equal to g minus b2 over m v squared. Now, the nice thing about this then is I can simply call v squared equal to something else, and I'll just call it y for now. Right? So what happens in this case then is what? I've now gone from having a single linear velocity on the left-hand side and a quadratic velocity on the right-hand side to now simply the same thing on both sides. So now I'm going to rewrite this then as 1/2 dy dx is then equal to g minus b2 my. Where then I can multiply both sides by 2. So let's put a 2 here, let's put a 2 here. From this case, I can then again use my integrating factor. Since I use that now, let's go ahead and talk about that. So I'm going to rewrite this then as dy dx plus 2 times b2 over my is then equal to 2 times g. So in this case, my integrating factor will be mu is equal to e integral 2b2 over m dx, which is going to be the same thing as e to the 2b2x over m. So good. So from here, multiply both sides by that. So my left-hand side becomes simply my total derivative. So then I'm going to get d dx of then mu times y is then equal to 2 times g times mu. Or again, I'm going to integrate both sides with respect to x. So let's go and do that. Now, again, let's work with the limit that v initial is equal to 0, just to make it a little bit easier. So in this case, this guy's just going to cancel him. So the left-hand side is just going to become mu times y. And then the right-hand side is then going to be 2 times g integral of mu dx, integrated from x initial to x final. So good, let's go ahead and do that. So let's plug in our mu is. So again, our mu was, so again, an e to the 2b2x over m times y is then equal to 2 times g times the integral from x initial to x final, dx e to the 2b2x divided by m. So again, integrating this guy, I'm going to divide. So I'm going to get a 2g times m divided by 2b2. And then I'm going to get an e to the 2b2x divided by m, evaluated from x initial to x final. So here my 2's are going to cancel. So I'm going to get a gm over b2. And then I'm going to get an e to the 2b2x over m minus e to the 2b2x initial divided by m. So that's this guy. Now, since I want only y on the left-hand side, I'm going to multiply both sides by the exponential, but with a negative sign. So finally what I get then is that y, which is equal to v squared, is then equal to mg over b2, 1 minus e to the 2b2, we put a negative sign out front, x minus x initial, all divided by m. Or finally, taking the square root of both sides, I get v is equal to the terminal velocity times then the square root of 1 minus e to 1 minus 2b2 divided by m times x minus x initial. So this is then my, again, position as a function of time. So in this case, notice that this guy will only go to my terminal velocity when the position goes to infinity. And in that case, again, my velocity goes to terminal velocity, which is simply a constant. So good. So this then is my example, again, of air resistance or of air drag. So in this case, we're looking at vertical motion, again, in the linear and quadratic cases. And again, we see that our expectations, again, are correct based off of our physical interpretations, where again, and no matter which case we're looking at, again, for light times, it should just grow linearly in position, and that the velocity should go to the terminal velocity, regardless if the initial velocity is bigger than or smaller than that of the terminal velocity. All right, so I'll make one more video for Friday, and then I'll be back on Monday. I'll see you guys then.